Well, hello, everybody. So, time for a new topic, and this topic is called implicit differentiation. And I use that term because that's the common accepted term, and if you were going to try to find information about this elsewhere, that's what it would be called. Okay. Um, the I'm inclined to say that the procedure for doing this is not that hard. Okay. It's still calculus, and for that reason, like some people might see it as difficult. But I think what's harder might be understanding the concepts behind it all, and that's true with a lot of things that I tell you about. I might say, well, I'm going to explain the concepts. Uh, this might be the difficult part. It might make it seem more difficult than it actually is. And then we go to the procedure, and you might catch on to the procedure more easily. So I'm going to leave it up to you. I think that I should explain the concepts and I should explain the procedure, but I'm going to let you take away from that what you need and ask any questions that you have. Okay. So the reason why we call this procedure implicit differentiation is because, hold on, my cat is visiting me right now. All right. The reason we call it implicit differentiation is because there are explicit functions and then there are also implicit functions. Okay. So, an explicit function would be something like this, these typical formulas that we've been used to dealing with up to this point. If you look at, well, say, what's a function? A function is something, anything. It could be a formula, it could be a rule, whatever, where you put one x in and you get one y back out. That's what a function is. Okay, so if you look at this first equation, if I was to plug in an x and I did the calculation, it would tell me what y is. One x in, one y back out. Okay, and same thing with this other one. If I was to plug in an x, I'd have to do all the math. I might even need a calculator, but then I would get one y back out. Okay, so those are explicit functions. Now, on the other hand, if we have something like this, it's still true that if I plug in an x, I can get a y back out, but the equation doesn't do that directly. Okay, and another way that you might think about that is it's not, I'm having cat problems tonight. Okay, she keeps walking on my writing tablet. Um, so the equation isn't solved for y. It's not like I just plug the x in and get the y back out. There's still a way to do that, but it's more complicated, and it doesn't just, it's not like x goes in and y comes back out. So that's why we call this an implicit function. Okay, so implicit. Now, we like to find derivatives in calculus because they tell us how variables change together. They tell us how change in one variable causes change in another. Um, and our technique applies to derivatives of these implicit functions. Okay, all right. So let's look a little bit further into this. Here's the way that we might develop our procedure. So let's say that y is an implicit function of x, okay? And what's that mean? It means that if I give you an x, somehow there's a way to figure out what y is. X goes in, y comes out. But notice that I put this question mark up there, okay? Like this, because I'm saying like, well, the way you do that's not obvious. I don't have some equation where it's solved for y like that, and you just plug the x in, you get the formula, and you do the math, and you get y. So that's just the concept I'm trying to get across. Now, I want to talk about how you would find the derivative of y if it was an implicit function, okay? Meaning that y wasn't solved in terms of x or something like that. I want to do that by comparison. So But look at these two and just kind of compare one versus the other. Okay, so what's the derivative with respect to x of 1 minus 2x all to the fourth power? Well, to find the derivative of that, we would use the chain rule. Okay, and the chain rule goes like this. We bring this power 4 to the front like that. We take away 1 from that power. That makes it a 3. And then this part is the derivative of the thing inside there. Okay, and the derivative of 1 minus 2x is negative 2. Now, like, have that in mind and think about, well, how would you find the derivative of y to the fourth power where y was some function of x it's not specified, it's not entirely known. We know that it is a function of x, but we don't have the formula at hand, okay? Then it wouldn't really be any different, okay? Like this y right there, it could be something like 1 minus 2x. It's just that we don't have it, all right? We don't have that information. It's not solved that way. All that we know is it is a function of x somehow. So my claim to you is, why would it be any different? It's like these are the same thing. It's just that we don't know what y is supposed to be. So we'd say, well, same rule. You would bring the power down the front, you do the 4 like that. Then you take away 1, you get 3. And then you multiply that times the derivative of whatever is there. What's the derivative of y? Well, since we don't really know what it is, we'll just have to say y prime. Y prime being the symbol for the derivative of y, okay? So that's how we approach it when we deal with y being some unknown but implicit function of x. Okay, now that right there is the basis for the whole procedure. Okay, so right now I'll give you the procedure for how we're going to find y prime, the derivative of y with respect to x. Okay, so we write y prime, but we could also say dy over dx, right? We do that. They mean the same thing. So here, let's talk about how we find the derivative of an implicit function. Now, at this point, I'm just going to give you the instructions, and you don't have to think about it all theoretically like I was doing on this previous page if you don't want to, okay? It says this. Say we have an equation like this, where we want to find y prime or dy over dx. We want to find the derivative. So we got that equation. The procedure is to take the derivative of each term on each side of the equation with whatever rule is appropriate. But we multiply all y derivatives immediately by y prime. The reason we do that is because it's basically the chain rule. This right here, that's why we do that. Okay, so that's the first step, and then the second step is you solve for y prime, and then you know what the derivative is. Okay, so let's try that. This example says find dy over dx, otherwise known as y prime, for the equation 7x squared minus 3y to the 6 is equal to 2. All right, so I'll break that down into the same steps. Okay, so the first step and the second step. So the first step was to take the derivative of every term on each side with whatever rule is appropriate, and you multiply all y derivatives by y prime. Okay, so I'm going to write like this. There's my equation, and this d over dx, that's shorthand for saying I'm going to take the derivative with respect to x. Okay, all right, and I have to use whatever rule is appropriate. So first, for 7x squared, what's the derivative of 7x squared? That would be 14x. Okay, and then what do the rules say about the minus? We just carry the minus down. All right, now what's the derivative of 3y to the 6th power? Well, we bring the 6 down, so we get 18, and we get y to the 5th power. But it says as we do this with whatever the appropriate rule is, we multiply all y derivatives by y prime. So then we say times y prime. Okay, the reason we do that, if it helps you, is because of this. This is our comparison. All right, now let's see, that takes care of the left-hand side. Now on the other side I have 2. So what's the derivative of 2? 2 is just a constant, so it has a derivative of 0. All right. Okay, so that's the first step. Second step, I need to solve, since I want to know what the derivative is, I want to know what y prime or dy over dx is, I'm going to solve that equation for y prime. And then if I solve it for that, then I'll know what it is. Okay. So, well, let's see. I'll go ahead and recopy it, although it's not entirely necessary to do that, but I want to start fresh. There it is. Now, I want to solve this equation for y prime. Okay, so right there you see it. And this will be done just with algebra. Okay. So if I wanted to solve for that y prime right there, I'd move this 14x over to the other side. So I get negative 18 y to the 5th y prime and negative 14x. Okay. And then if I want to solve for y prime, like so my goal is to take this equation, the one that you see there, and reduce it to say something like y prime equals this or that, then that would be my answer. So I would just have to divide both sides by 18 y to the 5th, okay? So here would be my answer. Well, I'm going to get a negative divided by negative, so I'm going to put 14x over 18 y to the 5th. Okay, 14x over 18y to the 5th. And then that would be it. I've solved for y prime, and for the most part, I have my answer. The only other thing is that we would like to give our answer in the simplest form, and so 14 and 18, those can both be reduced by a factor of 2. So I'll get my final answer. If I reduce 14 and 18 by a factor of 2, I'll get 7x over 9y to the 5th power. Okay? All right. And then there's our derivative. This tells us how y and x change together. Okay? So y and x are linked by that equation, this initial equation. We might want to know how change in x affects change in y, and that's what this derivative and all other derivatives tell us.